Hey there, Mrs. Hanson once again. We're going to look at our last topic, Le Chatelier's principle. In Le Chatelier's principle, just so you can see, we're at page 13, page 13 in our notepad on our chapter 6. So just to give us a recognized area where we're at, top of page 13. We're asked to state Le Chatelier's principle, nice French name. It says, if a chemical system at equilibrium is disturbed or stressed, the system will react in a direction that counteracts the disturbance or relieves the stress. This is what you need to write for our definition of Le Chatelier. If a system is at equilibrium and it is disturbed, the system will react in the direction that counteracts the disturbance. Think of that as an equilibrium process. Whatever you do to the system to upset it, the system counteracts that to relieve the disturbance. We'll see that there are actually 3 types of disturbances. The first of those 3 are concentration changes. What happens to an equilibrium if we change the concentration of reactants or products? The second type of stress is temperature. What happens if we warm up or cool down a reaction? We have to consider if that reaction is endothermic or exothermic to determine how a temperature stresses a system. And the third, what if we change the pressure? And this is really typical of gaseous reactants and products, because pressure, I want you to just think about collisions. To increase pressure, we need more and more collisions, more and more molecules create higher pressure. If you want to lower the pressure, you want fewer and fewer molecules. So Le Chatelier's principle applies in a stress, either changing concentration, changing temperature, or changing pressure. Those are 3 examples of stresses. How will a system counteract the stress so that it can get back to equilibrium? Whatever you do, it wants to do the opposite to get back to an achieved state of equilibrium. Let's take these one at a time. Let's talk about concentration first. Le Chatelier's principle, and looking at a concentration change. Here's a balanced chemical reaction in which I see carbon monoxide reacting with oxygen to form carbon dioxide. We're being asked to apply a stress. What happens if the CO concentration increases? What will happen to the direction of equilibrium? So think about that as a stress. You increased the concentration of a reactant. What is the opposite of more? Well, it's less, right? If you increase the reactant concentration, you want to use it up. So the system counteracts that. So if I add more, it wants to use it up. Now to use up a reaction, you've got to point away from it. So the system will shift away from the concentration change. When I added more carbon monoxide, I increased the concentration of one of the 2 reactants. Adding more reactant drives the reaction right. And what happens on the way? As you go towards the right, I'm using up the oxygen, so it will actually decrease. Because it's the other reactant, it gets consumed as it turns into product. And the concentration of carbon dioxide will increase because I'm pointing at it. The reactants are both being turned into the product. So the concentrations will adjust to achieve equilibrium again. So all concentrations adjust to get back to equilibrium. Adding more of a reactant forces the reaction to the right. Let's try this one. What happens if I increase the concentration of CO2? So this is my stress. The stress is increasing the concentration of a product. So if this is my stress, what will the system do to counteract that? Well, what's the opposite of increasing? It's decreasing. So the system will counteract that by using up the extra product. And how do you use up something? Product. Oh my, product. My mind got ahead of me. So here's the stress. This is how the system counteracts the stress by using it up. To use it up, you got to point away from it. So you're going to shift left, adding more product. To use it up, you shift left and you're going to favor the reactants. So as you favor the reactants, I'm going to make more of the oxygen and more of the carbon monoxide. So along the way, to use up the extra product, you point away from it to use it up. The carbon dioxide gets consumed and the carbon monoxide and oxygen get made. So their concentrations will increase. Adding more product favors pushing left to achieve equilibrium. What happens if we remove a product? Now here's an equation where I have C2H6O in dynamic equilibrium with C2H4 and H2O. Let's let the stress be removing a product. Let's just say that's going to be water. So the stress is removing water. Well, what's the opposite of removing? So to counteract the stress, you're going to make more. Do the opposite. And to make more product, you better point at it. So to make more, you're going to shift right. And as you shift right, you've got to consume the reactant. It will go down. And as you shift right, the other product actually increases as you make more of it. Removing the water was the initial stress that forced the reaction to proceed to the right so you could make more of the water. And in doing so, you consumed the initial reactant C2H6O and you made more of the other product, the C2H4. Le Chatelier, whatever you do to the system counteracts. Try these on your own and come back when ready and we'll talk together. Are you back? You must be ready to check. In which direction will the equilibrium shift with each of the following changes in concentration? Letter A, if we increase the concentration of SO2, that means you've increased the concentration of a reactant. What we want to do is to do the opposite. The opposite is to use up the excess amounts of SO2. To use it up, you better point away from it, and therefore the equilibrium will shift to the right. And in doing so, you're going to use up the oxygen, and you're going to make more SO3. That's letter A. How about letter B? Letter B says, let's increase the concentration of SO3. So that's my stress. What's the opposite of more? Well, it's less, right? If you add more sulfur trioxide, you want to use it up. And so you're going to shift to the left to consume the extra product. And in doing so, you're going to make more oxygen and SO2. All right, shall we do letter C? What if we decrease the oxygen? So the stress now is decreasing O2. Well, what's the opposite of less? Well, that's more. So the system is going to want to make more, and you got to point at it if you're making it. So the reaction will shift to the left. And in doing so, you use up the SO3 and you make more SO2. You have one more. How about letter D? Decrease the SO3. So now the stress is decreasing SO3. What happens? Well, the opposite of less is more. So you're going to point at it to make it. So along the way, you're going to use up the SO2 and use up the O2 to make more of the SO3. And in doing so, you shifted that reaction to the right. Kind of intuitive. This takes a little bit of thought. If you add more, shift away. If you add left, shift towards it. Let's talk about temperature next. When the temperature is increased, the reaction that absorbs heat is favored. And we know that absorbing heat is an endothermic process. Let's say, for example, N2 plus O2 forms NO in an endothermic reaction. So I'm going to balance that equation, and I'm going to include the delta H to make this a thermochemical equation. In an endothermic reaction, heat is being absorbed. How does increasing the heat affect the direction of the equilibrium? I want to challenge you really to just invite the heat into the balanced equation. If this is an endothermic process, and it is, heat is required for the reaction to go. If heat is required, I want you to just treat it as a reactant. Write it into the equation on the left side. So let's rewrite this by saying it requires 43 kilocalories of energy to react with the nitrogen and oxygen to form two NOs. Heat is required, therefore treat it as the reactants. They're required. So requirements go on the left side. Invite it into the equation and treat it as a reactant. Treat it as something as necessary for the reaction to occur. Now it becomes quite easy in predicting the reaction. If the stress says increase the heat, if we increase the heat, the system wants to counteract that. To do the opposite, it wants to use it up. So we would say to use it up, you have to point away from it. And so therefore, the direction shifts to the right. Adding heat of an endothermic reaction shifts the equilibrium to the right, so it can consume the excess heat. In this reaction, we found that an endothermic reaction pushes to the right to alleviate the excess heat. If we have an exothermic reaction, let's take a look at this equation. Here we have N2 reacting with H2 to form NH3. We need 2 N's and 6 H's. And if I write this as a thermochemical equation, I just write that by tallying the kilocalories at the end of the equation. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. And along the way, in an exothermic process, heat is released. That's why we see a negative sign. Since this is exothermic, heat releasing, just like the products come out of a reaction, treat it as the product. Invite that in to the product side, and let's rewrite that. When nitrogen and 3 hydrogens react in a dynamic equilibrium, out comes 2 ammonia, and out comes 22 kilocalories of energy. Now, I didn't change this sign to mean that it's endothermic. That's not what this means at all. It means in addition to, and out comes 22 kcals of energy is being released. So that's an and sign, not an endothermic, but an and. This and that comes out of the reaction. I like to write it on the product side because if I increase the heat of an exothermic reaction, I can see that it's a product side, so I need to point away from that, and we now see that the reaction would shift left to alleviate the excess heat. Increasing the heat of an exothermic reaction drives the equilibrium to the left. If you have an endothermic, which means you have positive delta H, just simply write the delta H value on the left side of equation. And if you have an exothermic process, meaning the delta H is negative, write the value of the delta H on right side of equation. And just predict it as we did using concentrations. And I think that becomes very easy to do your shifting left or right just based on looking where the heat comes from. All right, let's look at some more examples. Here we have some molecular art. Our equation says A2 plus B2 yields 2 ABs. If T1 is greater than T2, is this reaction endo or exothermic? So this is warmer, this is colder. Well, let's see what's happened to the products. I have one, that's all I find. And how about B2? Looks like I have 2 of those. And in terms of AB, I have 1, 2, 3, 4, 5. Alrighty. So this is at T1. Let's tally what we have at T2. Here's A. Oh, it looks like I have 2 of those now. How about B's? We have 1, 2, 3 of those now. And, well, that's not an equal sign. I just got a little lazy and didn't do my double arrows. And how about the product? 1, 2, 3 products. Well, what happened? I can clearly see that the reaction proceeded this way because the AB got consumed. And I made more of A and B. So I can see the reaction shifted left, which means that the heat had to be over here. Well, no, wait. Because we actually cooled the reaction, didn't we? We cooled the reaction. So if the stress is taking heat out, we forced it this way. Look at this over here. If I write heat as a reactant, just put that word there, heat, on left side of arrow. And now look what the arrow has done. The stress was cooling down, so we removed heat energy. That was our stress. The opposite of less heat is more heat, so we want to point at it to make more, and we point at it by shifting equilibrium left. This reaction is endothermic. By cooling an endothermic reaction, you shift the equation left. When time went by, in terms of T1 to T2, we said this was a cooling process. So the stress is to remove heat energy. If the heat is written on the left side, it's a required. we know that heat must be present for the reaction to occur. So heat being absorbed is an endothermic process. Taking away heat, the system will counteract to make more heat. So it's going to shift to the left. That is an endothermic process. Wonderful. Let's try another. The reaction of sulfur dioxide with molecular oxygen forms sulfur trioxide, SO3, and it's an exothermic reaction. Well, let's get these to balance first. Here's 2 and 2. 2 sulfurs, check. 4 plus 2 is 6 oxygens, check. There's our equation, and it's exothermic. So I'm just going to write plus heat on the product side. Exothermic, heat is released, just like the products come out of an equation, heat is coming out. So write it on the product side. This is how I would represent an exothermic reaction with heat being released. Remember, this is not an endothermic sign. It just means and. What's coming out of the equation is sulfur trioxide and heat. Heat is being released. Which direction will the equilibrium shift if the temperature is increased? So here's my stress. I'm increasing heat. To use up the extra heat, I point away from it. So in letter A, the equilibrium shifts to the left. And in letter B, it says, what if it's decreased? So now the stress says, well, let's remove heat. You better point at it to make more. So you can see that this reaction would shift right. There is a third stress in Le Chatelier's principle, and that's pressure changes. When the pressure is increased, the equilibrium shifts in the direction that decreases the number of moles in order to decrease pressure. Think about this. A good note to write down. Pressure is really just defined as the number of collisions against the side of the container. So you can see the more and more and more molecules you have inside a container, the more and more collisions you have, the higher the pressure. So first, we look at a balanced equation to decide how many molecules on each side of the arrow. So in this example, as we write down, N2 reacting with 3 H2s to form 2 NH3s, a combined total of moles of reactant is 4, and a combined number of moles of product is 2. This side has fewer molecules than this side. So what if we increase the pressure? If the stress becomes increasing pressure, to counteract that, you want to do the opposite. The counteracting of high pressure is low pressure. And to achieve low pressure, you want the fewest number of molecules. So the side with fewest molecules becomes favored. Which side had the fewest molecules? Oh yeah, right here. Increasing pressure is going to drive your reaction to the right to decrease the number of molecules, so you have fewer collisions and thus have dropped the pressure. When pressure is decreased, the equilibrium shifts to the direction that will increase the pressure. All right, so let's say this. Here's the stress. The stress is lowering pressure. You do that maybe by putting it in a bigger container so that it's traveling further before it collides. So to counteract the stress, you want to do the opposite. You want to raise the pressure. And to raise the pressure, you want to favor the side with the most molecules. The side with the most molecules is the left side, so that would force the reaction to the left. The direction of the equilibrium when pressure is produced shifts to the left to make more molecules to create more pressure. Alrighty, shall we try some? Here's an equation. They gave us a structural formula. Perhaps we could rewrite that together. C2H2 reacts with 2 molecules of hydrogen in a dynamic equilibrium to form C2H6. And as I tally this, we have 1 plus 2. This is 3 moles on the left side and 1 mole on the right side, just comparing the number of particles on each side of the arrow. In letter A, it says, what if we put a stress on the system, and that's to increase pressure? So to counteract that stress, you want to lower the pressure. And to lower the pressure, you need to favor the side with the fewest molecules. And which side is that? Well, it's this side, isn't it? So for letter A, you're going to push to the right to drop pressure. And you can see then letter B would be the exact opposite, wouldn't it? If the stress is the stress is to drop the pressure, you want to counteract that stress by raising the pressure. And to raise the pressure, you're going to favor the side with the most molecules. Which in this example is the left side of the equation. How about and again? You want to try next one on your own? Here's an equation where we have a dynamic equilibrium. C2H4 plus Cl2 creates C2H4Cl2. We have 2 moles of molecules on the left side and 1 on the right side. What if we raise pressure? The counteraction would be to drop the pressure. And therefore, you're going to favor the side with the fewer molecules. Which side has fewer molecules? Well, in this example, it's to the right. And working through the opposite of that, if the stress is to drop the pressure, you counteract that stress by raising the pressure. And to raise the pressure, you favor the side with more particles. And the side with more molecules is the left side on this equation, so you would drive the reaction left by dropping pressure. I have one more practice problem, kind of bringing it all together. Let's take a moment and just think about true and false. Take a quiet moment, pausing the video, and read through this problem and just try. Is it true or false? And then come back to me when you'd like to hear my out loud thinking. All right, welcome back. Let's label each as true and false. Well, first I have to get a handle on my equation. 4 moles of ammonia with 3 moles of oxygen makes 2 moles of nitrogen and 6 moles of water. This is an exothermic reaction. I want you to know heat is released. And so I'm going to put and heat. Just to represent exothermic, exo, heat is a product. We remember learning endo means heat is a reactant. And not necessarily true, but I mean, heat is coming out of a reaction just like products do. If heat is being absorbed, it's necessary to drive the reaction, just like a reactant needs to be present to start a reaction. Heat is a starting material. It belongs on the left side of an equation for endothermic. And now I can look in letter A, if the temperature drives the equilibrium to the right, increasing the temperature drives equilibrium to the right, true or false? Well, if the stress is increasing heat, the opposite of that is to use up the heat. You want to shift away from it to use it up. So this is false. You would actually shift left to use up the extra heat. How about a next one? Letter B, doubling the concentration of N2. If I increase the concentration of N2, yeah, that's going to force it to the left. That's a true statement. The system will counteract by using up the extra amount. Increasing the pressure by adding an inert gas like helium has no effect on the direction of equilibrium. That's true. The inert gas will not participate in affecting pressure overall. I don't know, it might have been tricky. Increasing pressure by adding an inert gas like helium has no effect on the direction of equilibrium. That's a true statement. And the best explanation I can say is the term inert means it does not participate in the equation at all. How about letter D? Removing water. Well, if that's our stress, removing water is a stress. The reaction would force to make more, and so that's a true statement. How'd you do? This one might be tricky. I'm going to let you digest that for a little bit. The term inert means does not participate, no participation. And therefore it does not affect. So that's a true statement. Oh my goodness, look what we've done. We've made it to the end. You have a little bit of reading to do in section 6.7, looking at the effect of temperature on the homeostasis of the human body. Pull out 4 to 5 most important details from reading, and you've got your notepad complete. Congratulations, you've made it through chapter 6. I look forward to getting your note pack submitted, looking at your Connect and your chapter quizzes all coming up.